So yesterday and the day before, we have made some sum up of what are quantum gases in general, what is Bose-Einstein condensation, how it can be described, how the quantum gas can be described with the Bose-Pitevsky equation with weak interactions. And today and tomorrow, we will concentrate on the case where the atoms are confined to 2 dimensions strongly. And you will see that it will change qualitatively some of the properties of our quantum gas. So this is the lecture of today. So there, you see there is a third lecture, lecture 3. So of course, today and tomorrow we will go through lecture 2. And so then my time is over in principle. So I'm trying to negotiate if I can give you a 5th lecture or kind of seminar lecture on Friday afternoon if you're interested, on a basis for those who volunteer to listen to this point. We'll see also with the organizers if that's possible. But I let you know tomorrow if we do that or not. Because I will not be able to do this, to do the full program today and tomorrow. Okay, so in 1 or 2 dimensions, the fact that we constrain strongly the degrees of freedom of the gas changes qualitatively the physics. And typically what it does is that it enhances the role of fluctuations, either thermal or quantum. And also the topology is not the same. If you are in 1D, you are not allowed to, when you are in the metro, when you are in 1D, you are not allowed to go in front of the others to go faster because there is no transverse dimension, so it has some consequences. And also in 2D, it changes the fact that you cannot, if there is a pillar, you have to go around, and that's not the same thing as if your arms are stuck around this pillar, you cannot free yourself. Whereas in 3D, you can always go around and do like that. So the consequences is that in 1D, there is what is called integrability, and that means that there are no real thermalization of a 1D gas. The excitations of a bosonic 1D gas are a fermionic character, and the interactions are renormalized. The topological defects like solitons play an important role in 1D. So this is all what I will not describe because this lecture is about 2D. But, we have here somebody who has done her PhD in 1D quantum gases. So if you're interested, you can also discuss with Mathilde. She has studied a long time ago. She has studied quantum fluctuations, thermal fluctuations in 1D gases. In 2 dimensions, you also have no true long-range order. So this is something we will look at right now. And that's in 2 dimensions that you have the quantum Hall effect or the fractional quantum Hall effect, and a specific transition to a superfluid. This is called the Kosalith-Thouless transition, and that we will describe in this lecture. The interactions are also now renormalized, and the topological defect that play an important role in 2D is not the soliton, it is the vortex. So vortices are very important in 2D. So let me give you some example where the restriction to 2 dimensions has a huge impact on the physics in another field of physics, in condensed matter physics, and this is the quantum Hall effect. So quantum Hall effect concerns a 2-dimensional electron gas. So you confine strictly the electrons in a material to behave only along 2 dimensions by changing the different semiconductors to have big gaps. And so the motion of the electrons is strictly 2D. And if you have contacts here and you have a current passing through the sample between source and drain, then what will happen is that if you apply a transverse magnetic field, you will observe a transverse potential. So this is also true in classical physics in 3D. So the Hall effect is known for more than a century. But what's happening in 2D is that the transverse Hall resistance, which is a ratio between this transverse voltage and the current that goes through the sample, is quantized. And it is quantized in terms of a quantum of resistance, which is h over e squared, so with all the fundamental constants, h and e. And so this is the first observation of this effect, where when you increase the magnetic field, you have steps for the resistance, very, very well defined. And that's with this method that people do metrology of voltage or resistance, because it is so well defined, this plateau of Hall resistance, that it can be used to define what is a volt. And if you increase the magnetic field even further, you have a quantum of this Hall resistance, which is even not an integer number of the Hall resistance h over e squared, but a quantum of that, like 1/3, 1/5, etc. And this is possible only because your sample is confined in 2 dimensions. So without interaction, this corresponds to the quantum Hall effect, and for the fractional quantum Hall effect, interactions are needed. Okay, so this is just an example to show you that 2 dimensions changes the physics. Concerning what we will deal with in these lectures, 2 dimension is a very special case. It's a kind of marginal case. You remember when we were looking at either BC or not BC, 2D was kind of critical because you had to have this exponent q strictly larger than 0, and in a box in 2D it was 0. So it did not condense, but almost, I mean. And so in 2 dimensions there are lots of logarithms, lots of divergences, but only logarithmic divergences, and this plays a very important role. And finite size effects will save the game in a sense. So in 2D, we know that there is no BEC at strictly positive temperature. Bose-Einstein condensation is recovered in a trap. And in fact, what we will see is that interactions will save the game and induce a quasi-long-range order. So no true long-range order, but a quasi-long-range order with some not too fast decay of the first-order correlation function. And so this will allow us to still have a superfluid in 2 dimensions, even with almost no BEC fraction in some cases. Another important point is that in 2 dimensions, there is no true length scale for the interactions. So with the 2 dimensions comes also a scaling invariance, which explains the fact that the equation of states does not depend independently from the chemical potential and the temperature, but only on the ratio between mu and kBt. And also explain the fact that the monopole mode, so the breathing mode of the gas that we have seen yesterday, is not damped and has the same frequency whatever the amplitude. Whereas yesterday we derived the eigenmodes in the limit of small amplitude, remember? But for the monopole mode in 2D, we can go to any amplitude in a harmonic trap, and it's still 2 omega. And finally, there are specific things related to topology. So I mentioned quantum vortices. And there is an analogy with the quantum Hall effect for gases that are set into rotations, which, if I have time, I will discuss Friday, as well as a similar transition to the Kosallis-Aoulé transition for the vortex lattice itself. And this is my topic of research, in fact, and this also may be on Friday. All right, so how do we do that? Well, it's true that we live in 3D, so we do not have the atoms natively in 2D. So to have them in 2 dimensions, what you do is you build a trap such that you confine very strongly the atoms along one of the 3 dimensions of space. And so in this case, the degrees of freedom of your gas will be frozen along the dimension, the transverse dimension that I will call Z, and only the motion along X and Y will be relevant. So this is true as long as the temperature is very small with respect to the energy splitting between the transverse levels, so you don't have enough energy to populate the transverse states due to thermal energy, but also you do not have enough energy to populate the transverse states in terms of interaction energy. So you need to have the two conditions. The temperature and the chemical potential are much less than the transverse degree of freedom. So to be precise, this would be the chemical potential of the 2D gas has to be much less than h bar omega perp. Because if you compute the one of the 3D gas, of course, there is the energy of the transverse degree of freedom, which is on the order of h bar omega perp. So this is a 2D chemical potential. Example of realizations include optical lattices. So if you have a standing wave, then you have a lattice with a period that can be very small on the order of the wavelength. And as the trap is very thin, it confines strongly the atoms in 2 dimensions. And this is what is realized in optical lattices. So you can be even more clever and have what is called an accordion lattice, where your standing wave, you produce it by interfering 2 beams with some angle. This, of course, changes the period of the lattice. And you can start with a small angle and a long period. And then once your atoms are loaded in 2D, you can increase the confinement by increasing the angle, and then it compresses the gas, and you go even further into the 2D regime. And this has been realized in the group of Jérôme Meunion at Collège de France in Paris. Okay. Another solution is to use a 2-dimensional surface traps. So here, what makes a confinement is the fact that you have a total internal reflection at the interface between a prism and the vacuum. And this produces an evanescent wave at the surface of the prism. And again, an evanescent wave decays very fast on the scale of lambda over 2 pi. And if you have one red detuned beam that attracts the atoms to the surface, plus a blue detuned beam that prevents the atoms to stick to the surface, so just in between you have a minimum. And in fact, this configuration was the first one in which a 2-dimensional quantum gas was produced with atoms in the group of Rudi Grimm in Innsbruck in 2003. So my pointer, yes, it works. So this is this situation. And this is another example we do in our lab, where you use a magnetic field, a quadrupole field, plus a radio frequency field that selects a isomagnetic surface on which the atoms have to be trapped. And again, as it is a surface, it is something very thin. And so the atoms live on, in fact, the surface of a bubble in space. And because of gravity, the atoms fall at the bottom of this bubble, and this gives you access to a quasi-2-dimensional gas that you can probe. And what is nice in this geometry is that the trap is extremely smooth, and it's wonderful geometry to study the collective modes without any damping induced by the trap. So just to mention, these adiabatic potentials can also be used to try to populate a full bubble once you compensate for gravity. And this is also something we do in the lab, except that nobody up to now has been able to populate the full bubble with a quantum gas because there are intrinsic difficulties. And the only way to date to do that is to have another quantum gas inside and put the second quantum gas around the first one, but it's not exactly the same situation. Okay. So now, what is the plan for today and tomorrow, after this introduction, is to look at what does that mean, this quasi-long-range order in 2 dimensions, and then look at this Berezinski-Kossalev-Thouless mechanism to reach superfluidity, or to undo superfluidity, And finally, to discuss the scaling symmetry in 2 dimensions with the monopole mode and the equation of state. The references for the lecture of today and tomorrow. There is the proceedings of a school I organized in Les Houches 22 years ago, 2003, where many relevant lectures to this topic, the lectures by Zora Shapnikov, Ivan Castor, Maxime Olshani, Sandro Stringari, Ignacio Sirac, and Benoît Dussault. Then there is a very nice review paper by Emmanuel Bloch, Jean Dalibard, and Wilhelm Zwager about many-body physics with ultra-cold atoms. Again, this I already mentioned to you, the lectures at Collège de France by Jean Dalibard, which, if you are from Latin language, are readable, and there are all the equations and figures, of course. And the Nobel lectures by Michael Kostalitz and Duncan Haldane, because, yes, I forgot to mention, but I will come back to that. They received the Nobel Prize in 2016 together with David Thales for the specific features of the Kostalitz-Thales transition in 2 dimensions and the topology in 2-dimensional systems. So there are many more references, but in these different sources, you will find also lots of references that may be useful to you. All right, so let's now go to the blackboard. And before I look at the the quasi-long-range order, let me remind what's happening with BEC or not BEC. So if we go to to 2 dimensions, in the 2D uniform case, 2D box if you prefer, then the density of state that you get by taking the integral over dr dp of the Hamiltonian, which is p squared over 2m minus e. This guy gives you a density of state that is independent of the energy, because it does not depend on R, okay, so it's just the volume or the area L squared divided by H squared for R. And this P, as the energy depends only on the modulus and not on the angle, I can make the change. This is 2 pi P dP, which is just a pi times du if U is P squared. So I can make the integral, and I will find essentially a U minus epsilon. So the integral over U will just give me 1, just a delta of 1. And so with the prefactor, the correct prefactor, you have 2 pi m because of this pi and because of the 2m. But the density of state is just constant. So it has to also be, of course, greater. Epsilon has to be positive, so this is a Heaviside function to ensure that epsilon is positive. So this guy is 0 for negative epsilon and 1 for positive epsilon, okay? Just ensure that. So of course we can compute the number of atoms in the excited states, or the number of atoms, in fact, because you can put all of them in the excited states. So this is the integral between 0 and plus infinity of d epsilon of a constant. times our density, our population in state of energy E, which is exponential beta epsilon minus mu minus 1. So this one we can sum as we did always as being the sum between 0 and infinity of sum over n e to the minus n beta epsilon e to the n beta mu. So the n beta mu does not depend on epsilon. I can put it here. Well, here. I can put it outside the integral. And the integral over epsilon, okay, I need to multiply by n beta and divide by n beta, and then I just have 1. So it is 1 over n beta, or if you prefer, kt over n. So I find L squared 2 pi m kt over h squared sum over n of e to the n beta mu over n and this guy here is the inverse of the square of the de Broglie wavelength. And this is a yes, wait a minute. Yes, well, this in fact is just the logarithm of 1 minus exponential beta mu. I could have done it directly, in fact. It was not very clever to, because this you can write under the form. You can write it like that, and this is the derivative of logarithm of 1 minus this guy. Okay. So first logarithm, if I this is the atom number. This is the area. So n divided by L squared is the density. And so I can recast that in the form of phase space density, which is n lambda de Broglie squared, is equal to the logarithm of 1 minus exponential beta mu. And so what you find is that this atom number you can put in the excited state is not limited. Because even if mu goes to 0, then this thing here diverges. So you can put as many atoms in the excited state you want, and there is no condensation. But notice that we encounter our first logarithm. Okay. In a trap, the density of state, in fact, you can compute it easily. It's proportional to epsilon. In fact, it's epsilon over h bar omega squared. And so now when you want to do the integral, it does converge. And it gives you, once you compute it, I will not do it here, a critical maximum atom number in the excited state, which is also the critical atom number for BEC, equal to pi squared over 6 kBT over h bar omega squared. So, okay, in principle, above this number, or on the other way around, you can also write KBTC, which is 1 over pi h bar omega square root of 6n. This is the same thing. I just put it here on the other side. So below this temperature, you have BC. But now let's look at what is the density in the trap. So density or phase space density as a function of the position. And in fact, to do that, I can go back to this expression, or this sum, and replace mu by mu minus V over R. So the local mu. If I take a local mu, then I can do exactly the same trick. And what I will find is that the local phase space density, or the local density, if you prefer, is equal to the logarithm of 1 minus exponential beta mu minus V over R. So I take the convention, so the maximum value for mu is the minimum value for the potential. But if you have, you are going to the condensate, then mu is reaching this minimum value, so which corresponds to the center of the gas. Let's say that it is at a 0 position, for example, if we put 0 at the minimum of the potential. And then at this position, if mu is equal to V of 0, then again I have my divergence. So even if I am supposed to have a BC, the density at the center to be able to have a BC, so the density in the ground state, if you want, is infinite and diverges logarithmically. So here you see that even if, okay, in principle it works, you face some strange things and again some logarithmic divergences. So of course it is not physical. What will happen is that if you try to put an infinite number of atoms or an infinite density at the center of the trap, they will start to interact. And so your initial assumption, which is to write everything without any interactions between the particles, is wrong. And so this means that in 2 dimensions, you cannot ignore the interactions between particles. You really have to take them into account, and they will change qualitatively the results. Okay. A second remark I would like to make, and I will come back to that in more detail a bit later, is that if we try to write the GPE equation in 2D, what will happen? Okay, let me be brave and just write it. I h bar time derivative of psi is equal to minus h bar square over 2m Laplacian psi plus g 2d psi squared psi plus maybe some potential. And so remember, in 3D, we had G 3D, which was 4 pi a h bar square over m. And so what is the dimension of G in general? You know that we are dealing with an energy times psi. So G times psi squared is an energy. Or Gn is an energy. It is, in general, the chemical potential. So this means that G has a dimension, that the density is 1 over L to the power of the dimension. The dimension of G 3D is an energy times a volume. And of course, this is also true for G2D. G2D times the density is an energy so G2D has dimension energy times a surface. So with respect to G3D, it's a G3D divided by a length, okay? But now G3D is h bar square over m times a length, which means that my G2D has dimension h bar square over m. And I told you, okay, what characterizes the interactions in 3 dimensions is this scattering length, A, and this is very important. You can tune it, etc. And now, come on, we are left just with h bar square over m. There is no length anymore. So here is hidden this scaling symmetry. The fact that now there is no characteristic length for the interactions. And as there is no characteristic length, basically you can change the scale and nothing changes. So this we will discuss in more detail tomorrow. And so it has consequences on the monopole mode, and it has consequences on the equation of state. OK, so now let me start with what I promised, quasi long-range order in 2D. And first thing we need to do is to establish this 2D Gross-Pitarevsky equation and see a little bit what I have to put in front of this h bar squared over m when I confine the gas to 2 dimensions. So I have to remember I come from my 3D world, and what I do is to confine the atoms into 2 dimensions. So I consider the gas that is strongly confined along one direction that I will call Z. And then I have the 2 dimensions in the plane, which are X and Y. And I do that by having a harmonic potential along Z with a frequency omega Z. And I define the length corresponding to the harmonic oscillator, which is the size of the ground state, square root of h bar over m omega z. So what I will introduce is the fact that I expect now my wave function, my 3D wave function, to be the product of two independent wave functions, the one that confines along z, and the one that will describe my dynamics along x and y. So psi 3D of of x, y, z, I write under the form of my psi I'm looking for, which is a psi 2D of r times phi z of z. And here r I anticipate, and r is just the xy coordinates in the plane. And this phi of z is the ground state of the transverse harmonic oscillator. And this ground state is 1 over pi to the power 1/4 square root of az exponential minus z squared over 2az squared. So this is the expression of the ground state of the transverse harmonic oscillator. And so what I will do is plug this ansatz into the 3D Wojciechowski equation, and then integrate over the transverse direction to average over this direction to get an equation just for the motion in the plane xy. Okay, so let's do that. What do I have? I have I h bar d over dt of psi of phi xy phi z or I will maybe look at the ground state to simplify. So I will look at the steady state form of the Gauss-Pitevsky equation. So this is a mu 3D potential. And this is equal to minus h bar squared over 2m. And so my Laplacian is 3D, is just the sum of the Laplacian in 2D and the second derivative, sorry, it's a product of the two. Okay. But as phi z does not depend on x and y, in fact, it's just a product in this term. So the Laplacian acts on psi. And the same thing holds here. If I take the derivative of the product, in fact, this one is just just a number because it depends on x and y. And so this is just as applying it only on z. Now I have the potential. So the potential, what is it? It is the sum of a potential along the plane and the transverse potential of the, to confine the atoms in 2D. And then I have the interactions. So the interactions for the moment I am in 3D. So what is this term? So it's psi squared, psi, and then phi squared, phi. Okay. But now remember that phi z is the solution of the Schrödinger equation along z. So what we know is that minus h bar squared over 2m phi z plus 1/2 of m omega z squared phi z is equal to its energy, and the energy is h bar omega z divided by 2 phi z. So I can replace here this term here and this one by h bar omega z over 2 phi z psi. And I can put it on the other side because I already have a phi z psi here. Okay? So I'm left with mu 3d minus h bar omega z divided by 2 is equal to, and then I will multiply by phi z star. So is equal to phi z squared psi, if I multiply by phi z star on the left. And then I have to multiply by phi z star, so I also have one here, minus h bar squared over 2m Laplacian of psi phi z squared. And I have the potential, same story, plus v of r, psi phi z squared. And the interactions. So now I have to be careful because I already have a phi z squared, and I multiply again by phi star, so I have phi z to the 4th power. Okay. And now what I do now is to integrate over z. So that's what I said, like average over the transverse direction. I forgot to mention that you have an exercise for tomorrow for those who were not here. So I will let it here, because this I did not do in the lecture. So you can try to compute the value of the chemical potential in a trap, in a harmonic trap, in the case 3D and in the case 2D, in the Thomas Fermi regime. And I gave you 2 hints. So tomorrow afternoon, I give you the answer. Okay, so if I integrate now over dz the previous equation, I know that the integral of phi squared dz is equals to 1, because I have normalized the wave function like that. So each time I have a phi z squared, I have 1. That's not a big deal. But I have a term which is not phi z squared, and which is phi z to the 4th power. And so what is that? Okay, if I take to the 4th power, I have 1 over pi az squared, and I have exponential minus 2z squared over az squared dz, if I'm correct. Okay, and now, okay, I make the change of variable. I take u, which is square root of 2z over az, such that dz is az over square root of 2 du. And so this az, one of the az's go away, and I have 1 over pi square root of 2 az, the integral du of e to the minus u squared, which is square root of pi. So my pi at the denominator becomes square root of pi, and I find 1 over square root of 2 pi az. Wonderful. So now I just plug that into this equation. So this is 1, this is 1, this is 1, and this is 1 over square root of 2 az. And what I find is my Gross-Pitevsky equation so all the terms with 1, they give me the easy terms which are linear in psi. And the last term gives me the interactions, G3D over square root of 2AZ psi squared psi. So now you see that what I told you in a quick way before, that our chemical potential, our two-dimensional chemical potential, is the 3D chemical potential from which I have to remove the ground state of the transverse potential because it's a kind of sea over which we live. And so now the chemical potential I will use is always this one, which is a 2D chemical potential, okay? And second remark, the interactions, the G2D is equal to G3D over square root of 2 pi AZ. And now I can use the value of G3D, which is 4 pi h bar squared A over M. So 4 pi is square root of 16 pi squared. If I divide by 2 pi, I have square root of 8 pi. And so I find that it is h bar squared over M, G tilde, with G tilde square root of 8 pi A over AZ. So as promised, I have a dimensionless interaction constant, this G tilde, in units of h bar squared over M. And this dimensionless interaction constant is basically, within some factor, the ratio of the 3D scattering length to the size of the transverse confinement. So be careful here. This holds only if this interaction constant is small. Well, if A over AZ is small, which means that if A over AZ is small, it means that the scattering length is small as compared to the size the atoms have in the transverse direction, and it's still relevant to describe the collisions as being 3D collisions, because A is a 3D scattering length. So I could not do that if I confine so strongly that also the collisions happens in 2D. So here I am assuming that the collisions still happen in 3D, and that the scattering length is still relevant. And in this case, I have this G. But strictly speaking, I am a little bit cheating here. I should really look at the two-dimensional scattering problem, look at the amplitude, etc., and solve the problem. And here is a thing I don't think will have time to discuss with you, but is the origin of what is called a quantum anomaly. So in principle, there is no length scale in 2D, but in fact, if you confine so strongly that also the collisions happen in 2D, you have a 2D scattering length that enter in the problem. And as there are, in principle, no length scale, in fact, the collisional properties, they depend on the density. So it's a kind of scattering length that will depend on the density. It's a bit weird. This is 2D, okay? And in general, you are not sensitive to that in the experiments because it's really hard to have a confinement that is smaller than A. If we don't have Feshbach resonances, the order of magnitude of A is a few nanometers. And for AZ, well, of course, it depends on the transverse confinement. But you can remember the easy rule for rubidium, 100 hertz, 1 micrometer. And its K is last square root. So even if I have 10 kilohertz, I have 100 nanometers. And so you see that even in this case, AZ is still much larger than A. So the only way, basically, experimentally to have the other situation is to have a Feshbach resonance and increase the scattering length strongly such that it reaches almost 1 micrometer or something like that. And in this case, you have access to this physics of beyond 3D collisions and quantum anomalies. Okay, it was just a parenthesis. All right. So remember that we will assume here essentially a G tilde that is less than 1 in most of the situations. All right, so now let's go to the estimation of the coherence of the 2D gas in the degenerate regime. Degenerate means that the phase space density is significantly larger than 1, okay? Okay, so to estimate a little bit the coherence of our sample, the relevant function we have to look at is the one-body correlation function. Okay, so sometimes I apologize in advance. Sometimes I will write G1 with a big G. Sometimes I will write G1 with a little g. And that's not good because normally you normalize it in one case and not in the other case. But I will mix everything. But I'm sure the people from quantum optics will do a much better job. But in my notes, it's a little bit mixed. So let's put G1 like that. Normally, the little G1 is normalized. So it's 1 for independent particles at 0 distance. And the big G1 is not normalized and has the dimension of a density. Okay? So I will take this one. So for thermal gas, and something I would like to say before is that this G1 is, what is this G1? It is the average of the wave function taken at position R with the wave function taken at position R prime. So it is the average value of psi dagger R, psi R prime. So why is it called this decay, the coherence length? Because if these guys are a wave function that expand everywhere, then this thing here has some well-defined phase. And the other one also has a well-defined phase. And so when I take the scalar product and take the average, I have a complex number, but with a well-defined phase of modulus 1. And so the coherence length is infinite if I can write this as some wave function with a very well-defined phase. Whereas if there are phase fluctuations, then if R prime is far from R, the phase at R prime will not be correlated with the phase at R. And then when I take the average, it will smear out, and the value will be 0. So this is what measures the coherence length of the sample and how much it decays with the distance R minus R prime will give me some notion of a size of the coherence in the sample. So for a translational invariant system, of course, this thing depends only on of R minus R prime. If you are in a trap, it depends on the position R and R prime. So for our problem, for the moment, we will consider atoms with a uniform density on average. So for a uniform gas, it depends only on R minus R prime. And so you can write it as G, and it is in general isotropic, so you can just write G of R, where R is the distance between the two particles you pull. And so in the case of a thermal gas, and last thing I have to say is that G1, the correlation, the first order correlation function, is a Fourier transform of the density distribution. Of the momentum distribution. For this uniform case. So if you have a very narrow momentum distribution, it means that the uncertainty on momentum is very, very narrow. And you can describe your sample with a wave function which is essentially with the same phase. And in fact, they are completely linked. So the width of the momentum distribution will be h bar over L if L is the coherence length of the sample. So they are related like that. So this state, now if I take a thermal gas, the momentum distribution is a Gaussian with a width which is square root of m kBt. And so the G1 function is also a Gaussian, because the Fourier transform of a Gaussian is a Gaussian. And with the width h bar over square root, well, h basically over m kBt. And this is, in fact, within a factor, this is the thermal de Broglie length. And so the G1, in fact, is the density times exponential minus r squared over lambda dB squared. And there is a pi factor somewhere. I don't remember if I wrote it. Yes, here. Because of the h bar and the h. Okay. So this is the case for a thermal gas. So of course, a Gaussian decays very fast, even faster than an exponential. So what it tells you is exactly what we have discussed in the first day, it tells you that the coherence of your wave packet is given by the wavelength. And that's exactly what describes Bose-Einstein condensation. When I made the little drawing, each atom has a size lambda dB. This is what it means. For an ideal gas in 2D, in fact, it can be shown that G1 decreases exponentially. So I will not redo it here, but this is what we find for a non-interacting gas. Okay? Ideal gas means non-interacting. And this is a very general, in fact, theorem in 2D that tells you that there is no long-range order. So even in the degenerate regime, ideal gas in degenerate regime, okay? So even at very low temperature, there is a theorem that prevents long-range order to exist. So it means that even with our interacting particles, even if we introduce interactions, it will still be true that there is no true long-range order in 2D, and if we go far enough, there will be no phase correlations. But now, what does happen in our 2D interacting gas in the degenerate regime? So for that, we will, as we go to the degenerate regime, we will describe the 2D gas with classical field. And we will write the wave function under the form of a modulus linked to the density times a phase and what will maybe give rise to the drop of the G1 function will be the fact that there are thermal fluctuations either in the density or in the phase that will make the wave function far away too different from the wave function at position R. So to describe our problem, we will take a box of size L with periodic boundary conditions such that we can use Fourier decompositions of our modes. And first, we will discuss if that's more density fluctuations or phase fluctuations that will be a problem. So let's estimate the possible density fluctuations. In fact, these density fluctuations will cost some energy, of course. they cost interaction energy. Because if you have some fluctuations of the density with more atoms here and less atoms there, then the interaction energy here will become to grow because you put more atoms at the same position. And so we should estimate what are the relative strengths of the interaction energy and the temperature to see if there is a chance at a given temperature that the gas accepts to have more interaction energy and fluctuations. So the interaction energy, if I estimate it and compare to temperature, I have the interaction energy, which is on the order of g squared times the density, h bar squared over m, of course. And then the temperature is 1 over kBT. And again, I find here that I recover the expression of the wavelength squared. So this is 2 pi g tilde n times the Debreu wavelength squared. And so this is the phase space density. And I assumed that the phase space density was larger than 1, was large. And so this will be large for a phase space density large enough. If I go to very low temperature, then the phase space density increases, even if g tilde is not very large. 2 pi times g tilde will be of order 1. And then if the phase space density is large, this ratio will be large. So the fact that there are interactions, this will prevent fluctuations of the density. And so density fluctuations are suppressed. And so what we will do is we will assume that the density is uniform, N0. We neglect all density fluctuations. And all the fluctuations, we put them in the phase theta. So square root of N0, uniform fixed density, and only theta can vary. Okay, and now we assume that theta fluctuates because of the thermal energy. And in this description, we will again assume weak fluctuations, kind of wave-type fluctuations, which neglects vortices. But still, we will be able to access the quasi-long-range order. So we will decompose the variations of theta on modes, which are essentially plane waves. And for that, we use the fact that we are with periodic boundary conditions, so we can write theta as a sum of the different possible modes with some weight, e to the I kr. So we decompose, we Fourier decompose the variations of the phase. So theta is real. And so if theta is real, it means that it is equal to its complex conjugate. So if I take the complex conjugate, I have a ck star and e to the minus ikr. So it means that ck C minus K is equal to CK star. Okay? And now what we would like to do is to compute G1. So what is G1? G1 of R is the average, so I can take with respect to 0. It is the average of phi 0 phi of R and this means that it is the average, it is N0 times the average of e to the I theta of R minus theta 0. Okay? Where I've written explicitly the phase difference between psi and psi of 0, psi of R and psi of 0. And so as we have this average to compute, in fact, this you can expand with the sum, the formula, the expansion of the Gaussian. And what you will find is that this is the average of 1 plus I, the average of theta minus theta 0, plus the average of theta minus theta 0 squared over 2, blah, 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 blah. And in fact, all the odd terms, they will average to 0. And you are left with only the even terms, which will have a theta minus theta 0 squared average over 2, and then the same over factorial 4, etc., etc. And in fact, you can show that this is equal at the end to exponential minus 1/2 the average of theta of R minus theta 0 squared. So the RMS average of theta minus theta 0 squared. So this is what we need to compute now. This is our goal. Compute the RMS value of the phase, how much it spreads, and this will give us the length over which G1 decays. Okay? All right, so now we have to write this average. And now if I replace theta by its value, theta of R minus theta of 0 squared is the sum over k and k prime of ck e to the I kr minus 1, because if I put r equals to 0, this just gives me ck, and then ck prime e to the I k prime r minus 1. So I use the fact that ck prime is equal to c minus k prime star. is equal to, yes, that's it. And so this, I will be able to write it under the form. I do the sum on minus k primes instead, okay? I can do it with the minus k prime, so let me put directly the minus. And then I will write that C minus k prime is C k prime star. So I will have C k prime star e to the I kr minus 1 e to the minus I k prime minus 1. But the modes are independent, and so only the contribution with k equals to k prime will stay. So when I take the average, so the average of my theta squared is just the sum over k, and then I have the average of modulus of ck squared. And then I have to take k equals to k prime here, and so this gives me 1 plus 1 minus e to the I k r minus e to the minus I k r. Oops. And so this is equal to 2 factors of 1 minus cosine kr. Okay. Now what I have to do is to estimate what is the value of k squared. And for this, I need to know more or less what is the energy that allows the phase to fluctuate. So what is the typical energy in each mode, etc. And so for this, I need to know what is the energy corresponding to my wave function psi, and where I can put kt in there. So this is h bar squared over 2m, the integral of gradient of phi squared. And then there is the interaction energy, for which we have said that these modes will be prevented because the interaction energy is too large as compared to the thermal energy. And so we have the gradient of phi. The gradient of phi is the gradient of theta in modulus. So this gives us h bar squared over 2m and 0, the integral of the gradient of theta squared. And phi squared is just n0, so this is n0 squared times the surface, so this is just atom number divided by 2 g tilde h bar squared over m n0. And so what we have here, the gradient of theta, what is it? The gradient of theta is the sum over k of I k ck, e to the I k r. So what is the gradient of theta with independent modes? The gradient of theta squared. It is the sum over k of ck squared, k squared, because, again, the modes are independent, and so the k and k prime, they just cancels. Because these modes are independent, and so if you compute the average then with the sum over k and k prime, essentially these, the integral over k and k prime, the fact that they are independent will tell you that they are orthogonal if k and k prime are not equal. And so when you do now the integral, you just get the surface again, L squared, because this now does not depend on R. That will go with the N0 and give you N. So the energy is the interaction energy, and then this sum over k of ck squared k squared. And 0, yes. And so the reasonable assumption to estimate the ck squared is to say that, okay, we have an energy 1/2 of kBt per mode k. Up to some cutoff energy Kc. That could correspond to having a too large energy, again, as compared to the interaction energy. And then it means that we would like to write that this sum is in fact a mode, sum over the case of some energy Ek times Ck squared, and this would be n times a sum of 1/2 of kBt. And so the energy that comes into this sum is written there, and it's n times h bar squared k squared over 2m. And so this times c, okay, sorry, this, yes, this times ck squared is 1/2 of kBt, which gives us an estimate for the average value of ck squared that we needed. And which is 1/2 of kBt divided by Ek. With this value for Ek. All right, so now I just plug this into my expression here. And I find for theta of r minus theta 0 squared. So the 2 and the 1/2, they go away. So kbt. And the sum over k of 1 minus cosine kr divided by n h bar squared k squared over 2m. Or if I put the 2m, h bar squared, etc., n in front, it will be 1 over n, 2m kbt over h bar squared, sum over k, 1 minus cosine kr. And this is, again, the double wavelength. So this is 4 pi over n times the double wavelength squared. And the sum over k, I can replace by some integral. dk, sorry, I forgot the k squared here. Dk 1 minus cosine kr over k squared. And to replace by the integral, I need to put a 1 over 4 pi squared L squared here. Okay, and n over L squared, now it is the density. So the 4 pi, etc., becomes 1 over pi. Well, maybe I let it for the moment because I will have here 2 pi k dk. So yes, 4 pi and 4 pi squared, it's 1 over pi. There is a 2 pi, so it's just 2. L squared over n, this is a density, so I have here n0 lambda de Broglie squared. And I'm left with the integral over k dk divided by k squared. It's dk over k, 1 minus cosine. No, because here, sorry. I still need to keep the phi because I have k r and there is the angle. So there is a 2 pi I need to put back, and a d phi between 0 and 2 pi. Yeah. Okay, anyway, in fact, this guy here at the end, I think, does not contribute because it averages, if I am correct. So I have to check that because I've been a bit fast in my notes, but okay. So I think at the end, we are just left with this one. And the one here will give us back the 2 pi of the angular integration. So I think this one does not contribute. This one gives us back the 2 pi. And the integral, here we see that we need to set the boundaries now. So it has to be integrated between some k min and some k max. Because again, what I see, I have a 1 over k to integrate. So what is a primitive of 1 over k? Logarithm. Oh, what a surprise. And so what I find is that this will give me the 2 pi, so will give 2 over the phase space density d. And then I have to integrate this guy here, which gives me a logarithm of K max divided by K min. So what are the boundaries? So the lower boundary for these wave-like excitations what is it? Well, you are supposed to look at excitations between the point 0 and the point distance by a distance r. And of course, it's not relevant to look at wavelengths that are above this distance. So your minimum kind of period you have to consider is r itself. And this gives you a lower cutoff for K min, which is basically in 1 over r. So let's say pi over r. I have 1 r here between 0 and r. So this can be the estimate of the minimum boundary. And for K max, this will be limited by the maximum energy you can consider, and this depends a little bit if you have a temperature which is above or below the chemical potential. Typically, you have to have your K max such that energy should be below the temperature or the chemical potential, depending which one is larger. So this will give you some typical cutoff length scale for the high case, which will be either the double wavelength -1, if it is kT, or the healing length -1 if it is mu. So this is for in the case where this is a temperature that is larger, and this is in the case where this is the chemical potential that is larger. And this will give you the cutoff. Okay. So now I have to replace the expression for this variance of theta in the G1. And so G1 of R was the exponential of minus, so it's N0 times the exponential of minus 1/2 of this. So the 1/2 removes the D, the 2 here, it's just 1 over D. And then I have the ratio between K max and K min. So let me call, let me call lambda T. Let me say that this K max, I will write it under the form lambda T, and the lambda is either lambda dB or xi, depending on the situation. And so I find that it is exponential minus, so 1/2 with 2 go away, 1 over D, logarithm of K max, which is pi over lambda T, divided by K min, which is pi over R, so logarithm of R divided by lambda T. I have the exponential of the logarithm. I can put it below. And so I find that it is N0 R over lambda T to the power 1 over D. So in other words, if I put it the other way around, it's lambda T over R to the power 1 over D. And this is the important result I wanted to derive. So what does this say? It says, first, that the coherence length is maybe on the order maybe it's set a little bit by this lambda, but not really, because there is this exponent here. And so if I wonder, okay, what is the distance over which g is 1/2 of the value at the origin? Or at the origin, it diverges. So this is true only for r, which are not too small, okay? So it is true for r larger than lambda t, essentially. So if I have r equals to lambda t, this is n0, okay? But then when do I get 1/2? This is for lambda t over r to the power 1 over d is equal to 1/2. So r over lambda t to the power 1 over d is equal to 2. And then I take r over lambda t. This would be equal to 2 to the power d. And so r is lambda t times 2 to the power d. Okay, and we are in the regime where the phase space density is large. So it's exponentially large, this coherence length, when we go deeper and deeper in the degenerate regime. In other words, this G1 of R, it's sure it decreases. It decreases. So if you go to infinity, this is 0 for sure. So it's true there is no long-range order. But if we are in a degenerate regime, so if it is not degenerate, it goes 1 over R, okay. But more and more you're degenerate, less and less it decays. And with a size of your system, if it is a finite size system, it is really reasonably small. And if the system is smaller than 2 to the power d lambda t, then even at the edge of the system, it will still be with a large value of G1. So this is called a quasi-long-range order. And the key point is that the correlation function decays algebraically and not exponentially or like a Gaussian. So it decays very slowly. And as it decays very slowly, it extends the coherence enough for important properties like superfluidity to establish. And so in reasonably finite-sized systems, you can still have an important fraction of the gas that is still condensed because the correlation function decays only algebraically. So I will just draw the summary. At t equals to 0, you can have a true BEC. Then at very large phase space density, you have a quasi-long-range order with an algebraic decay of G1. When you exceed some point, we will see that there will be a region with an exponential decay. So this is with like 1 over R to the power 1 over D. So here there will be a regime with some exponential decay. And in the thermal limit, it's Gaussian. With the typical size given by the Dobrev-Wade legs. And so what we will see next time is the transition associated to that, which is a Kosterlitz transition. This will be for tomorrow, I'm afraid. Okay, let's stop here.